Monday night, and I'm sure people have grander plans than spending the evening with me. Okay, so we made very good progress before. Yeah.
You said that you are what are we doing with G and H?
Yeah.
So is it that we are like one of those G and H is the characterization function of the filter, and the other is the input function?
That's correct. Right. It's essentially, yeah, that's exactly right. The question is, what do they mean, G and H? And right now we're just putting arbitrary numbers in there, just to make just to test the mathematics out. But eventually, the H will be the impulse response of a filter, and the G will be the signal itself that's going through the filter. So now you've essentially computed what the result of the filter is. Okay, so I want to pose another question. Before, we argued that, so let's say you have a signal G that's of length n, and a signal H that's of length m. And you want to take their linear convolution using the FFT method. So how many zeros should you pad each one? How many zeros should I pad G? Yeah, exactly. So this will get padded by m minus 1, and this will get padded by n minus 1. Exactly. So now both of these will have the length of n plus m minus 1. Now, is this the only value that you'd want that you could pad it to? Is there something magic about that number? It's the minimum. Could it be more? What would happen if you did more? But would you get the wrong answer? Why might you want to pad it more? Right. So one of the magic properties of the FFT is that it's basically designed to work with signals that have length of power 2. Right. So it works for length equals power of 2. And in fact, I suspect that behind the scenes in MATLAB, in places where you can't see, if you ask it to do an FFT of a signal of length 5, it's really padding zeros until it's of length, 16, and taking the DFT of that 16-point signal.
8.
Or 8, whatever, okay. You're right. Maybe it does 16, I don't know. Right, but yeah, 8 would make more sense. So essentially that's happening anyway, but were you to write your own from scratch FFT, that's essentially what would be going on. So in reality, there's nothing that says you can't pad it to beyond the minimum. And in fact, it makes more sense to to pad G and H to the nearest power of 2. The nearest power of 2 that's greater than n plus m minus 1. And all that will happen is when you're done with the computation, you'll have a few extra zeros tagged on the end that you just ignore. Right, and actually David and I did an example of that during the break before we started messing around with my voice. So, does it still remember what G is? All right, so here's G and H. All right, so both of them now have way too many zeros on there. So now if I take the inverse FFT of the FFT of G1 times the FFT of H1. Yeah, let's try that again. Everybody got that except for me. There we go. So you see we got the right answer, but because I put 3 too many zeros, I wind up with 3 too many zeros. Do I care? No, you just ignore them, okay? So that's not a showstopper. Good. David, what's the story with the dot next to the multiply sign? What's that doing there? Yeah, okay. I didn't mean to pick on you. Just want to make sure that that's something I wanted to make sure everybody got that. If I didn't do that, what would happen? Right, it'll give you an error because essentially these are two row matrices of the same size, so they don't follow the rules for matrix multiplication. Over and over again, right? Well, right. Yeah, it'll drive you nuts. And actually, it really drives you nuts when if you wind up with a complicated function where your independent variable appears more than once, for example. Then you have to remember that everything is dot times, dot divide. Otherwise, you go loopy fast. Okay, so we got that out of the way. We're actually almost to the end. So actually, I'm going to backtrack a little bit before we answer the last. So the last three questions on the paper were about overlap add and overlap save. But I think before we mess with those, I just want to do a few more examples. Let me just check my code real quick. Some of these I might just. Oh, we can look at these actually. This one's kind of cool. So some of the details that we've glossed over so far just have to do with the properties of the DFT. And I think this particular file, again, one that I'll post on Blackboard, this references table 5.1, which in my book, let me see if I can find that. Thank you. 258. So I'm looking at 258. So one of the things that the book tells us is that any signal can be broken up into even or odd. Or if it's complex, you can break it into a conjugate symmetric and a conjugate anti-symmetric. All right. So in this MATLAB file, I've just wrote some code to do that computation for you. So if you want to do I do it once with a real function, and then once with, a real sequence, and once with a complex sequence. I just pick the numbers kind of arbitrarily. So to get the conjugate symmetric form, it's just like we talked about this already when we talked about linear conjugate symmetric. If you want to get the conjugate symmetric portion, you take x and you add that to the conjugate of the time reverse copy of itself and divide by 2. And then for the anti-symmetric part, it's x minus the conjugate of the time reverse part of itself. So here's x. Actually, let's clear this. Control A. Clear all. So okay, we'll do this the old-fashioned way. So let's evaluate that. So again, this takes advantage of my circular flip command that I wrote, which hopefully everybody will be writing or maybe has already written. So here is x conjugate symmetric, and x conjugate anti-symmetric. So if we just look at these for a second, this is kind of cool because it just gives you an opportunity to think a little bit about what conjugate symmetric looks like and what conjugate anti-symmetric looks like. So the conjugate symmetric, right, first we have the 0th element. So that's just 1. So no problem there. So now we have the +1 element is 3 minus 1.5i. So the -1 element is going to be the conjugate of that. So it's conjugate symmetric. So the +1 element and the -1 element are complex conjugates of each other, which means they have the same real element, but the imaginary element is opposite. Okay, so that's good. So then we have the plus 2 element, which is this one, should be the conjugate symmetric of the minus 2 element, which is the same one. So for that to be the case, there can't be any imaginary part, right? Because I'm telling you that the imaginary part of this number has to equal the negative of the imaginary part for the same number. So that can only be with 0. So that's cool, right? That works out. That gives us, that shows us concretely what a conjugate symmetric signal looks like. And we can do the same thing for the conjugate antisymmetric portion. So the first number is 3i. Okay, so that's the 0th element. So now we have the 1 element and the negative 1 element, and those are conjugate antisymmetric, which means it's the negative of the conjugate. Is that right? It's essentially the imaginary parts are the same and the real parts are opposite, I think is how it works out. So you can see, and it's actually the same logic as before, right? So the 1 and the minus 1 are conjugate antisymmetric, and then the 2 and the minus 2 are conjugate antisymmetric, but that's the same element. So for the same reason that in the previous signal, the imaginary part was 0, now the real part has to be 0 right here. Okay, that's the only way that the real part can be both, the negative of itself. And then if I add those together, if I add together my x conjugate symmetric and my x antisymmetric, x conjugate antisymmetric, okay? So now I get my original signal x back. So any signal can be broken down to a conjugate symmetric and a conjugate antisymmetric. Okay, does anyone know offhand what should be the properties of the DFT of a conjugate symmetric signal? Should be real. Okay, so if I do FFT of conjugate symmetric, I should get real. Not bad. Okay, perfectly real. If I do FFT of antisymmetric, should be perfectly imaginary. Did it work? Sure enough. So,
you were saying this is the 0 element and this is the 1 element and minus 1. How did you?
How did I get that?
Yeah.
Oh, okay.
Why wasn't it 0, 1, 2, 3?
Well, it was, but it's so I'm arguing that. Let me just. Yeah, I'm using the modulo. I think you came in. It's just fine. I'm happy to just run through it again. It's modulo mathematics. Essentially, you're saying that if I take. So this is a signal of length n equals 4. So you can say that this is element 0. This is element 1, 2, and 3. But you can also say that if this is 0, so if this element is 0, then if you go to the left by 1, that you're actually going to come to here. Right, that's like a circular, you're doing a modulo. So if you go to the left by 1, you wind up there. So this is element negative 1, and element negative 2, negative 3, negative 4. And in fact, the easiest way to think about it is to put those numbers in a circle. So you say, what are my numbers? 4, 3, negative 1, 2, corresponding to elements n equals 0, 1, 2, 3. So then I could say, well, what is x of negative 1? Well, here's x of 0. So this is x of negative 1, x of negative 2. It just goes in a circle. That's a good question. It's worth, yeah, you're welcome. It's worth revisiting. Okay, so any signal, when you take its FFT, the FFT can have a real part and imaginary part. The real part always comes from the conjugate symmetric portion of the signal, and the imaginary part always comes from the conjugate antisymmetric portion part. Okay, which is cool, right? I mean, it's neat that always works out. So if you have a signal and if I tell you I have a real signal and I took its FFT and the FFT was real, what are you obliged to conclude now? But if it was real, that would be not only conjugate symmetric but also right. A real conjugate symmetric signal is even. Right. So if I take let's make up an arbitrary even signal. So 1, 2, 3, 3, 2. That's even, right? No? Yes? Okay, so now if I take FFT of x, it's real. So let's add that to our list of interesting things to remember. So, and again, we talked about this. Come on. All right, so we've got, so x can be broken down into conjugate symmetric and conjugate antisymmetric. And the conjugate symmetric portion corresponds to the real part of the FFT. And the imaginary bit, the antisymmetric goes to the imaginary portion of the FFT. All right, and if you add those together, you just get the FFT of x. And we also recall from before that if you have a signal that's both real and conjugate symmetric, that means even. And if you have a signal that's real and conjugate antisymmetric, that means odd. So if I tell you I have a real sequence, I took its FFT, and the FFT came out to be purely imaginary, you have to conclude that this signal is odd, right? It is conjugate antisymmetric, that's true, but if it's also real, that means it's odd. Yes?
When you are defining a signal as a real, so then how can it be conjugate symmetric? Means if you can define it as a even, but when we are talking about conjugate symmetric, that means the signal is complex.
Not necessarily. I mean, real signals are a subset of complex ones. So you can have a signal that's real and complex, symmetric and antisymmetric. So let's do an example.
Doesn't mean a real and conjugate symmetric signal is, can we say it as an even signal also?
Yeah, that's what I mean by this. If it's real and conjugate symmetric, that means it's even.
Oh, that actually I thought it was DFT even.
Oh, no. This is just, right. I mean, if it, remember, so conjugate symmetric means that x of negative n is the conjugate of x of n. So, for example, if x equals 1, 2, 3, 3, 2. So x of 0, no big deal, right? It's conjugate symmetric with itself. So now let's say x of 1 and x of negative 1. Well, x of 1, or x of negative 1 equals 2, which in fact is the conjugate of x of 1. Right? If I give you the number 2 and I say what's its complex conjugate? What's the complex conjugate of 2? It's 2, right? So that's why this works. It's conjugate symmetric and it's even because it's real.
Yeah, are you discussing the circular conjugate symmetry?
Yes. Oh, okay.
Conjugate symmetry?
Right. So all of this applies to circular. I'm sorry, that was important. I should have been more clear about that. But isn't it neat though? You come to MATLAB and this stuff just works. Right? If we create an odd signal, so So 1, 2, 3, negative 3, negative 2. So here's a purely odd signal. If I take its FFT, I should get something that's, that didn't work. I think the first element has to be 0. Yeah, there we go. Convolution, right. Right, the FFT corresponds to a circular convolution, or circular, everything's circular. It exists in the circular domain, we'll say. Right, so if you take a purely conjugate antisymmetric signal and take its FFT, you should expect something that's purely imaginary, which is what we get here. So this is, I'm just verifying some properties for you of these signals.
So if I take, I would have taken the DTFT of X, then it should not produce a...
If I do the DFT of X? DTFT of X.
That is what the... I think you are producing because that DTFT is not related with the circular convolution. That is, if you take a linear even sequence, I think.
Yeah. No. This would work. This would work. If you said x comma omega equals dtft of x. So x comma 1. I have to give it a denominator. Oops. Thank you. I would have figured that out eventually. Right, so plot omega comma omega divided by pi comma real part of x. Actually, let me do this. Subplot 211 plot grid on subplot 212 plot. Right, so the question was, how does this relate to the DTFT? So what I've done is I've taken that same signal that we just saw had a conjugate symmetric, sorry, it was odd, and it had a purely real DFT, and now I've taken its DTFT. And the top part is the real bit, and the bottom part is the imaginary bit. Yeah, I'd have to think for a little bit about what the relationship is. I didn't plot this because I knew what it was going to look like. I sort of plotted it to look at it to see if I could answer the question.
But if you were taking a linearly even sequence, I think you will get a purely even sequence.
Oh, right. If I took a linearly even sequence and then shifted it, I would still have to do the time shift in the frequency domain because you can't truly make an even sequence in MATLAB.
Yeah.
Okay. Right. Freak Z is making, yeah. Freak Z works in a linear scale. That's right. Did everybody follow that? Did I lose anybody? No. Okay. So the question was let's back up to the question for a second. The question was, I just did this example where I took a FFT of a circular odd sequence. It wasn't linearly odd, it was circular odd. Those aren't the same. We know why those are different now. I took its FFT, and the FFT had the property that we expected. The FFT was purely imaginary. Das's question was, what if you go back to freak Z now, right? What if you go back to the discrete time Fourier transform, of which the DFT should be a sample? What if you do that? And the answer is, so we tried that. I took the DTFT of this signal, and it was not purely imaginary. And the reasoning is that the DTFT we would have gotten an imaginary signal if we had a linearly odd sequence, but we don't have a linearly odd sequence here. We have a circular odd sequence. And I suspect they're related somehow, but I can't think of it off the top of my head. I think we could, let me play around with that. I might be able to sort of make something interesting out of that later on, but I think for the time being, we're satisfied to just leave it at that. Okay. What else are we going to pull out of this example? Okay. What property should so for any signal, we have sort of two options. We can break it into either conjugate symmetric and antisymmetric, or we can equivalently break it into its real component and its imaginary component. Right? That's another way we could break a signal. So x equals the real part of x plus j times the imaginary part of x. What property would we expect the Fourier transform of the real part of x to have? Should be? Okay, any other opinions? I'm not saying it's wrong, I just want to know if anyone else has an opinion. Okay, let's give it a shot. So Das predicts that if we take the Fourier transform of the real part of a signal, we should get conjugate symmetric. Conjugate symmetry. So let's try that now. So let's go back to so here's my signal. Oops. Evaluate. So I'm going to take the FFT of the real part of x. Okay, what is that? Is that conjugate symmetric, antisymmetric? Does everyone buy that? Okay, so here's the 0 element. The +1 element and the -1 element have the same real part and opposite negative parts, so that's conjugate symmetric. And then the +2 element and the -2 element are the same one, and that's purely real. So that's good to go. Cool. So let's try the opposite now. Let's try the FFT of the imaginary part of x. Right, the book predicts, so I'm on table 5.2 now. The book predicts, am I on table 5.2? No, I'm still on table 5.1. The book predicts that this should give me conjugate antisymmetric. What do I have? Is it conjugate antisymmetric? Really? Oh, actually, no, I don't know. I think it's conjugate symmetric. But the book says very clearly in table 5.1 that if I take the Fourier transform of the imaginary part, I should get conjugate antisymmetric. What do we do wrong? Yeah, the book says pretty clearly that it's not the, remember the imaginary part, this is actually kind of a cool reinforcement of something we tried to learn before. If I tell you the imaginary part of x, is that real? Is that a real sequence or an imaginary sequence? Ah, see? Right, if I say give me the imaginary, so here's x. If I say give me the imaginary part of x, it's real. And we've just discussed that if we take the FFT of a real sequence, it's going to be conjugate symmetric. Okay, so that makes sense now. So now I'm going to take the FFT of j times the imaginary portion of x, and what do we have now? That's better. That's conjugate antisymmetric. So let's go and finish my little table. So if we take the Fourier transform of j times the imaginary part of x, we should get conjugate antisymmetric. All right. So again, I think we sort of bit off the real conceptual stuff in the first half of this lecture. Now I'm just trying to sort of do twofold. I'm trying to give you a little bit of intuition about how these properties work, which certainly will come in handy somewhere down the line, but also just to show you that these are all things that can be verified in MATLAB. So it's just kind of trying to familiarize our vocabulary with how we can use MATLAB in just some straightforward cases. Okay, so that's the end of that example. So that example did real and imaginary and also symmetric and antisymmetric. So if I run that the same way you'll get it, what does it do? Okay. Right, so if you run this when you get home, you'll see that the FFT, the conjugate symmetric part, was real, the antisymmetric part was imaginary, FFT, the real part, was symmetric, FFT, the imaginary part, came out to be 0. Oh, that's because I'm dealing with a purely real function. And now if I hit return again, it's going to repeat the same thing over again, but now it's going to be operating off of a complex sequence instead of just a purely real sequence. And now we see the properties that we talked about before. So real, imaginary, conjugate symmetric, conjugate antisymmetric. Anyway, something for you to play with, to kind of convince yourself that I wasn't just doing too much hand wavings. Questions? No? Maybe? Okay, let me just look at this and then we will get to the overlap add and overlap save open. Let me just see what's in this file. I wrote these last week, so they're not totally fresh on my mind. Some of this stuff I might just be happy to leave it for you to play with. So this file I've called the DFT properties. And I think I will leave most of it for you to just to play with on your own time. But just to explain to you how it works. So, for example, if we go to, this is essentially verifying all the properties in table 5.3, I believe. Yes. So, for example, one of the second property on table 5.3. I'm just going to tell you now how to use this file so you can verify. So now we're talking about verify table 5.3 using what I call dftproperties.m. So at the top of the file, I've created sort of two arbitrary sequences, both of length 5. One called G, one called H. And for each one, I take its FFT. So now I come to the table, and the table tells me there's this property called the circular time shifting property. And what that tells me is if I take my signal G, and I take the Fourier transform of, so I'm going to take my signal and I'm going to shift it to the right by NO, N sub 0. So let's say I've got a 5-point signal and I'm going to shift it to the right by 2. So I started with G and I had its Fourier transform. Now I'm going to take G and shift it right. What's the effect on the transform? Well, the book claims that the effect on the Fourier transform should be that I take my original transform, G of K, and multiply it by W sub n to the minus K n0. And W to the n is one of these magic numbers that we talked about last time. I'm sorry?
Explain e to the power minus j to pi by capital N.
You remember it off the top of your head. Better you than me. W to the N equals?
E to the power minus j to pi divided by N.
N, I think that's right. Yeah, it's essentially the unit circle divided up into N equal places. Okay. So in other words, this is predictable. So if you go to the code now, I'm trying to verify that. So let's jump to the part where I've got circular time shifting. So here's omega n, Wn, sorry, just according to the formula. Here's my shift. So I arbitrarily picked a shift of 3. So now I'm going to compare two things. I'm going to take my signal, G. I'm going to circular shift it by 3, by N0, and I'm going to take its FFT. And what table 5.3 tells me is that that should be the same as my original FFT times Wn raised to the power of N0 times all my possible different values of K. So now I've got X1 and X2, and those should be the same. So what I do to test if they're the same, ideally, if they're the same, I should be able to subtract them and get 0. In reality, what happens is that there's always like this little mathematical rounding error between them. So instead of seeing if their difference is 0, I take their difference and I look to see if their absolute value is greater than epsilon. What's epsilon? 1 to the minus 9th. I just set that arbitrarily. So in other words, look, as long as the difference between them is less than some arbitrary small value, let's just assume they're the same. So you run this file, and it doesn't really do anything exciting. It's just that on the screen, it either tells you whether or not it succeeded or failed. And in all cases, they've been successfully demonstrated. So the interesting, if you were to play with this by yourself at home, the interesting thing is not so much what it gives you on the command line window. Like, of course, they're all going to work. Otherwise, A, they wouldn't be properties, and B, like, I wouldn't have coded them properly. So what's interesting is to go to the file, and you can just look now and see that, okay, well, this is how you're going to encode the, I'm sorry, I lost my place. That was the circular shift. Right, so now you can see how you, I'm sorry, I was up here. That's why I was lost. That's the MATLAB embodiment of what the circular shift should be in the book, right? And you can play with that and see if it makes sense. But they all work out to be the same. So this file just essentially verifies all the FFT properties. Does that seem reasonable? I mean, I feel like we could talk about it in more detail, but it's just going to wind up being a little bit pedantic, just kind of going through case by case. But it's worth, I like playing with those numbers to verify that these properties that they discuss in the book actually work. You know, if you circular shift it, there's a predictable effect on the FFT. If you, if you convolve two FFTs, if you convolve two signals, there's a predictable effect on their FFTs. So, and we can play around with that. So you might, for example, you might consider changing the signals or changing the lengths of the signals or trying to make the signals different lengths and see what happens. But there's some interesting stuff that you can, so it's a tool you can use to play with this stuff. Okay, questions? Okay. Let's sort of hit the last highlight for the day and then, so let's backtrack a little bit. So we talked about how to use the DFT method to convolve X and H. So now let's say that I've got live audio information coming off of a telephone. So X is really long. In fact, it's so long. In fact, it's so long that I don't really know when it's going to end. Right? So I'll leave it open-ended like this. So X is potentially infinite in length. My filter is very well behaved. Right? My filter H has some nice length to it. Now, in order to do the previous thing that we talked about, I had to take the FFT of h, the FFT of x, and multiply them. If x is infinite, how do I take its FFT? Okay. Right. Okay, so it looks like everybody's done the reading, and this makes me happy, right? Obviously, you cannot. So let's start with the obvious, right? So the problem is that we cannot compute FFT of an arbitrarily long signal, okay, of infinite length signal. Solution is we break it up. So break up x into small chunks. So there's two methods. Right, so you break it up into small chunks, and then essentially you're just computing the linear convolution of each individual chunk with the filter. So we had two choices. Right, one was overlap add, and one was overlap save. Okay, who can explain to me what overlap add is? Any takers? David has just volunteered. And Chris is going to get the next one, maybe? All right, sweet. Let's start with this. If I take my x, how do I segment it? Does it matter how I segment it? You're right. I mean, so first of all, nothing you said is wrong. I'm just trying to flesh it out now a bit more. So how do I sample this? Am I going to overlap my chunks? Right. So that's the trick to this, right? Overlap add uses non-overlapping chunks. Okay, so here's a chunk, here's a chunk, here's a chunk, and here's a chunk. And let's say each chunk is of length n. David, you said something that interested me. You said that x and h had to be the same length. Do they? What if they're not length? Like, let's say x was 100 and h was 3. Is that a showstopper? Yeah, you pat them both to 128 or whatever. Right, pat them both to whatever the minimum length is. Yeah, so it would be nice if they were the same length. Right. Exactly. Right. Exactly so. But yeah, I just wanted to relax your restriction a bit that these have to be the same length. Okay, so let's say that h has length m. So now I'm going to do my linear convolution between x and h. We'll call this x1 and h1. And what does that yield for me? How long is my result? Okay. So my first result is going to be like this long now. Okay, so we'll say that this is y1 and that has length n plus m minus 1. Is that visible? Very nice. Okay, second chunk, same length, right? Where does it start? So you can kind of see where the problem is that, so now I've got my second chunk, y2, which also has length n plus m minus 1. But interestingly, these two overlap. How many samples do they overlap by? Yeah. This is going to be m minus 1 samples wide. All right, so we can see that this is just going to keep going on and on and on, right? The nice thing is that we started with an infinite length signal, but we don't care now. We're just going to wait. First 100 samples, compute the FFT, do the convolution. Wait for the next 100 samples, compute the FFT. The only thing we have to be careful about is that when we get all these individual linear convolutions, we can't just stack them end to end because we have to actually take care of this overlap. So here's y3, and finally here is y4. So essentially, the final step, and the reason why we call it overlap add, is you're going to take this bit and bring it down as is. Let me just extend these lines down. This will all go up on Blackboard tomorrow. I'll print these notes onto Blackboard so that okay, so in essence, all the non-overlapping parts go into your final sequence as is. Had I drawn this a little less sloppy, they would have all appeared to be the same length. But then you have all these segments in between where there's overlap. And where there's overlap, you just have to add them together, right? So it's this bit plus this bit give you the chunks in between. Right, and that's why we call it overlap add. So again, it's conceptually not horrible, but you just, when you go to, I can't remember in the homework I asked you to implement either overlap add or overlap save. If it's this one, you just have to remember that when you compute each of those individual FFTs, you just have to remember to overlap them appropriately before you sum them together for your final answer. So let's see. If there's a clever question I can ask out of this. So let's say I have an audio signal and I decide to break it into chunks of length 100 and filter it with a filter of length 3. How long do I have to wait before I know what the 102nd element is of my result? You see what I'm saying? So I'm taking my signal, x, and I'm breaking it into chunks of length 100. All right? And I'm filtering each of those 100 chunks, those chunks of 100 with a filter of length 3. So the question is now, I'm very interested for some reason in knowing what the result is at sample number 102. How long do I have to wait before I know what that sample is? Do I just wait till after I have those first 100 samples? You have to wait 2 full cycles. That's exactly right. So for example, what I'm arguing is, let's say I want to know what the result is at this point in time, right? I can't know what that point in time is until I know all of y1 and all of y2. So I actually have to wait for 200 samples before I know what goes on at sample 102, for example. Okay? You ready, Chris? All right, let's have a whack at overlap save.
Basically, you need overlapping chunks in this segment. And you're going to take the circular convolution as well as the linear convolution.
Okay.
And the terms that are similar, you're going to keep, whereas you're going to disregard any result from this circular convolution that wasn't present in the linear convolution.
I'll take that. Okay, so does it matter? Let's ask this question. Does it so I'm going to take x and divide it into chunks that are overlapping. Does it matter how much they overlap by? If someone else knows, you can jump in. Does anyone else know? Okay, so there's a limitation on it, but it's not, you know, it still leaves you a little bit of wiggle room. Okay, so you have these overlapping chunks, and so now you've got your filter H. You've got another 5 minutes, then we'll go. So now you got your filter H. So you convolve X with H. So that gives you, let's see, Y1. And you're going to do a circular convolution, right? So we discussed before that when you do the circular convolution, what you've really done is you've taken the linear convolution and you've done some overlap. So some of those elements are going to be affected by the overlap, and some aren't. So essentially, and you can, if you know the length of the linear, if you know the length of each of the component signals, and you know the length of the circular convolution, you can predict every time which samples will be ones that were not affected by the overlap. You just keep those, and that's it. So you're essentially going to take the non-overlapping samples from the first convolution and the non-overlapping samples from the second convolution and the non-overlapping samples from the third convolution, and you just lay them end to end to end. So in other words, in the previous example, you had the overlap, in the convolved chunks. Now you're moving your overlap to the signal X, and you're removing the overlap from the summation point, so that you never have to add once you get the individual Y's. You just keep stacking them end to end. So let's ask this last question now. Let me just scoot forward in the book to the right page so I can make sure that we get this totally right.
So will it be correct output, right? If we disregard the...
Yeah, it'll be exactly correct. It'll be exactly the same as if you've done a linear convolution between X and H. Right. Let's try it like this. Let's say X is of length 5. My X chunks are of length 5. And H is of length I'm sorry, let's scrub the 5. I want it a little longer. Let's say X is of length 7 and H is of length 3. Is that better? Okay. And now let's say we're doing let's say now we're going to do a convolution of length, sorry, I'm just trying to find the right number here. So we're going to do a convolution of length 9, I believe. Is that how you do it? So it's going to be 7 plus 3 minus 1. I think is the correct way to do this. No, that would be... Right. So... No, I'm sorry. You want to do these of length 7, I think is what you want to do. You want to do a convolution of length 7, I believe. So if you convolve... If you do this function... Circular. So let's say we do this. Oops, not 3. H. So how many points of that result should be the same as the linear convolution? All 7 of them should be 5. How do you get 5?
We subtract m minus 1, which is the length of h. M is the length of h minus 1. This is the part rejected.
Right.
So should be 7 minus 2.
So we know for a fact, we can actually tell this, right? So we know that if we do a linear convolution between x and h, we should be expecting something of length 9, right? So we know the correct answer should be something like 1, 2, 3, 4, 5, 6, 7, 8, 9. But now we didn't make our circular convolution big enough to avoid an overlap. So what you're going to have is after 7, you're going to start to have a repeat. So let's see, 1, 2, 3, 4, 5, 6. So now you're going to have 1, 2, 3, and so on. And so over here, so the 1 is going to have an 8 above it and a 9, 7. So in other words, how many points do you have that are unaffected, that are the same as the linear convolution? 5. So those 5 points will always be the same as the linear convolution. So those are the ones, essentially, that will go into here now. So essentially what you're saying is, take the circular convolution between x and h, and then only keep elements 3 through 7, and then those are the ones that go in the first box. I'm sorry?
To recover first and second points.
Right. No, because now you're going to do, when you do the, so forget about 1 and 2. Let's just pretend that they're gone forever now. Let's worry more about getting elements 8 and 9. The way you're going to get elements 8 and 9 now is your next chunk, your next x chunk is going to overlap this first one. So that in the next chunk, these guys, the ones that are not affected by the circular convolution will now be sitting where 8 and 9 are. So then you'll know what 8 and 9 are. They'll be in the next. You'll get them from the next convolution. Right? So you say, oh, I can't get them from this convolution. They're covered up. They're obscured by the results of the circular convolution. But that's okay, because the next one you're going to do, there's some overlap. And in that overlap, that's where you'll get these elements. And the next time, these elements will be here.
Why not 8 and 9? Will they not come in place of 1 and 2? How will they come in place of 3 and 4?
I may have not correctly. I think it depends how much overlap you do. Right, that's the piece that's missing. No. No, there's another dimension to this that we haven't put in the diagram yet, which is how much overlap to put.
Well, I mean, for 1 through 9, is that the convolution of the big string with x and h?
Yes.
are using
Yeah.
So there's the 1 and 2 and 8 and 9, you throw them away, because the next sample of 1 through 9 is the next window and it's overlap, so you're shifting it over.
Correct.
And so that, if the overlap isn't enough, then that's enough.
Right, right, right. There has to be enough overlap that you're
It's all
guaranteed
tied.
it's all tied together. Does anyone know exactly how much that overlap should be? I seem to have, it's m minus 1. Right, so that would be arguing that you need to have at least, in this case, 2 points of overlap. I mean, the book does the example through in a bit more detail. I'm just trying to do the hand-waving approach to kind of convince you that it works, or at least try to give you some intuition why it works. I don't know if I've succeeded in that. The book actually does crunch the numbers in some detail to convince you that that happens the way it's supposed to happen. And I would direct you to page 275. But yeah, I think the trick is just getting a minimum amount of overlap, which I think is, I think it's m minus 1. It's just the length of h minus 1, and that should be, if you have that much overlap, then the next time around, samples 8 and 9 will now be in the middle.
We have that much of overlap because overlap add method, we computed the overlap is n minus 1.
Right, actually, and that makes sense. I just remembered the intuition. So, David, you were arguing originally that, look, if you just shifted by 2, then these points will wind up being here, and they'll be sullied again by the overlap. But that's, oh, you didn't make, maybe I thought that's what you said. But what happens is that you also have the filter h, which adds another length of 3, right? So if there's an overlap of 2, then elements 8 and 9 are going to be here, but then they're going to be shifted over by another 2 for another 2 on account of h. So that brings them to here. And now they're sitting in place of 3 and 4. So that's it. You just keep on trucking down the line. Again, that's kind of cool too, right? So now you don't even need to do any adding anymore. You just need to overlap your chunks of x, convolve, which we know how to do very quickly now, and then that's it. You're done with your answer. You put it in the queue and you say, now I know the next 5 elements of y, or the next 100 elements, whatever it is.
For given that delay is cumulative, means for each iteration there is two samples of delay is repeatedly added. So that's why it will.
Yes, there's always 2 samples of delay, or n minus 1.
Minus
1.
1.
Right, that's a good point. How many samples of delay are there? You wait. We had to wait. Our first chunk was of width 7, so we waited 7. We took the FFT, and then we started with number 3. So there was a delay from element 1. We got element 3. So there's a delay of 2. So your result is always at best 2 points behind your input. Yeah, so a delay of 2.
All is between the length of m and it's, you have to be careful how you put it.
Right. I would suspect you'd have to design that with a fair amount of care in order to get it so you don't accumulate unacceptable delays. So I think, right, what's the take-home message, right? Is the take-home message that in order to be a successful engineer, you need to know how to crunch, overlap, add, or overlap, save? I suspect the answer to that is no. I mean, I suspect that what you really need to take away from this is you sort of understand the principle of how it works, and you understand that if you had to write some MATLAB code to make it work, you could know how to do that. I mean, so the principle is valuable. The knowing how to code it up is valuable. I don't think there's anything inherently about this that you'll be a failure as a grad student if you don't have it committed to memory exactly what it is. It's more about, I think it's more just about understanding the process behind how do you break down a big signal and take its DFT? You can't, but you can think of a solution to do it. And as long as you keep track of the numbers, it should work out okay. Anyway, I think we should call it a day. The bus is going to leave soon. So I think we're just going to continue in the same loop. I'll put up new reading focus questions tomorrow, and I'll add another homework question tomorrow, and all the lecture materials from today will also go up tomorrow, so we should be okay. That's about it. If anybody has any comments about the class, I don't know if I've mentioned this before. If it's too easy or too hard or too